Hi students, I'll try in this educational video to carry out a tutorial showing how to determine the wind action applied on a building's wall based on Eurocode 1. Of course, as simply and as clearly as possible. Okay, let's go. So, we start by describing our problem. We have a rectangular plan building with a windward wall on which the wind is blowing, with also side walls and a leeward wall. And we assume that the air density is rho equal to 1.25 kilogram per meter cube. And this building has a certain characteristic dimensions, which are the crosswind breadth B equal to 20 meters, the in-wind depth D equal to 10 meters, and the building height H equal to 5 meters. And we assume a terrain category number 2. In Eurocode 1, we have 5 terrain categories 0, 1, 2, 3, and 4. And the terrain category number 2 means that the area is with low vegetation and isolated obstacles. And we consider that the loaded area producing the wind action is higher than 10 meters square. So we will use in our calculation CPE10 as external pressure coefficient. And we consider also that the building is without dominant face in terms of openings. We consider a basic wind velocity VB equal to 27 meter per second. It should be recalled here that the basic wind velocity is equal to a certain directional factor C directional multiplied by a certain season factor C season multiplied by a certain fundamental value of the basic wind velocity VB0. And this VB0 is determined based on the wind map, uh, which depends on the country and the wind zone inside the considered country. Now, in order to determine finally the net wind pressure, we start by determining the reference height. And for the wall, this reference height, denoted by ZE, is equal to H for the side wall and the leeward wall. And for the windward wall, it's determined based on the model that you see in the right of this slide. In our case, we have a building height H equal to 5 meters, and also we have a crosswind breadth B equal to 20 meters. So it's clear that the building height H is lower than the crosswind breadth. So we are in the first case of the model, and the reference height ZE is equal to H. Now for the terrain roughness, we start by determining a certain terrain factor denoted by Kr using the formula that you see now. And in our case, we have a terrain category number 2, so Z0 will be equal to 0.05. And if we apply numerically this formula, we obtain the value of the terrain factor Kr as 0.19. Now, based on this terrain factor, we can determine the terrain roughness using the formula that you see now. And for our case, reference height ZE equal to 5 meter is higher than Z minimum equal to 2 meters. This Z minimum is determined or is given by the table, as you can see. So we can use the formula highlighted here in red, and applying numerically this formula, we determine the terrain roughness CR at the reference height ZE equal to 0.875. And now we determine the mean wind velocity using the formula that you see. Here we already determined the roughness factor CR, and we have the value of the basic wind velocity VB. So it remains the orography factor. And the orography effect here is considered not significant in the wind velocity. So the orography factor CO at the reference height ZE will be equal to 1. And for the basic wind velocity, as I uh, explained at the beginning of this video, will be equal to a certain directional factor multiplied by a season factor multiplied by VB0. And we use often the value 1 for the directional factor and the season factor based on the national annex of the standard BS European norm 1991-1-4. So finally, this basic wind velocity VB will be equal to the fundamental value of the basic wind velocity VB0 as 27 meter per second. If we apply now numerically the formula of the mean wind velocity Vm, we will obtain finally 23.62 meter per second. Now we determine the wind turbulence using the formula that you see now. Also here we have a reference height ZE equal to 5 meter higher than Z minimum equal to 2 meters. So we can use the formula highlighted here in red. We use a turbulence factor K1 equal to 1 based on the national annex of the BS EN 9114 standards. And if we apply numerically this formula, we obtain a wind turbulence IV at the reference height ZE equal to 0.2171. We move to determining the basic velocity pressure. The basic velocity pressure is determined using the formula that you see now. And here, applying numerically this formula, we determine QB, which is the basic velocity pressure, as 0.456 kilonewton per meter square. We determine now the peak velocity pressure using this formula, and numerically we obtain the peak velocity pressure QP at the reference height ZE equal to 0.879 kilonewton per meter square. Now, for the external pressure zones, it's determined for the sidewalls based on the model that you see now in this slide. And here E is the smallest between the crosswind breadth B and 2 times the height of the building H. So E will be equal to 10 meters. And D, which is the in-wind depth, is also equal to 10 meters. So we are in the case where E is equal to D. So in this model, we are in the second case, which show two external pressure zones A and B on the side walls. For the windward wall, we have a zone D, and for the leeward wall, we have a zone E. Now, for the external pressure coefficient, they are determined based on this table provided by Eurocode 1. Uh, it should be recalled here that we consider it a loaded area producing the wind action higher than 10 meters square. So we use the external pressure coefficient CPE 10. And based on the ratio H divided by D, we can determine the line that we will use in this table. Here, H by D is equal to 0.5. So 0.5 is between 0.25 and 1. So we can use a linear interpolation to determine CPE 10, which are the external pressure coefficient in our case. And after calculation, we can determine these external pressure coefficient as detailed in the table that you see now in this slide. Here, as you can notice, the zone C is not applicable because we have only two pressure zones on the side walls, which are A and B. Now let's move to the internal pressure coefficient. We consider that the building is without dominant face in terms of opening, so the internal pressure coefficient CPI is determined using this model. But in order to use this model, we have to determine a certain factor mu. But in our case, it's impossible to determine mu. And in this case, the internal pressure coefficient CPI will be CPI minimum equal to minus 0.3 and CPI maximum equal to 0.2. Finally, we determine the net wind pressure as the difference between the external wind pressure and the internal wind pressure. And the wind pressure is determined as the peak velocity pressure QP multiplied by the pressure coefficient. And here, Zi, which is the internal reference height, it will be equal to the external reference height ZE associated to the faces that contributes with their openings to the creation of the internal pressure. And so ZE equal to Zi equal to 5 meters, and in this case, the peak velocity pressure will have the same value at the external and the internal reference height as 0.879 kilonewton per meter square. So here, the net wind pressure will be calculated as the most unfavorable value. The most unfavorable here means the greatest value. So in this case, this most unfavorable value of net wind pressure will be associated to the most unfavorable difference between the external pressure coefficient CPE and the internal pressure coefficient CPI. In here, this most unfavorable CPE minus CPI will depend on the most onerous CPI. Here, the most onerous CPI will be equal to minus 0.3 when CPE is positive, and it will be equal to 0.2 when CPE is negative. Why? Because the most unfavorable CPE minus CPI means the largest absolute value. And after calculation, we can determine the net wind pressure at each zone as it is detailed by the table that you see now. This educational video takes end. Please, if you have any remarks or questions, please don't hesitate to mention it in the comments. Thank you very much for your attention.